Is it? I have to turn this on. Does it have to be turned? Hello? Oh.
I guess it has to be closer.
Hello? Hello? There's the... Oh, there's a control for it?
Hello, everyone. We're going to get started. Coming up, we're going to have Bart Trojanowski. He's going to be talking about Git, distributed source control. And afterwards, we're going to have lunch. And then after the lunch, there will be a workshop on Git. It will be in 2405 Siebel, so just across the street. And hope you enjoy the talk.
Thank you. My talk is titled Tracking Code Changes in the Distributed Environment. And I'm mostly talking about Git today. So the first part of the talk, which is the one you're in right now, I'll be covering the introduction to distributed revision control systems, and I'll be using some terminology from Git, but it's mostly a generic talk about distributed revision control systems. All right, so about me, my name is Bart Trojanowski. I'm here from Canada. I spend my days using Linux, and more specifically, I use Debian. I work on Linux kernels for various of my clients. I write drivers and set up embedded systems. Most recently, I've been playing around with Android. I do most of my coding in C, which should be no surprise because I do kernel development. Most of the low-level system stuff is always written in C, but there are other ones that I play with also. I do my my development using Vim, and I track all of my code changes using Git. All right, so this is the table of contents for today's talk, and I'm going to go over SCN concepts in general. Then I'll talk about centralized revision control systems, decentralized revision control systems, and time permitting, I'll give you a very brief overview of Git commands. So source code management describes the process of multiple developers working together on a common code base. And it describes more than just the tools, but also the policies and the politics behind it, the processes. The tools that are used are revision control system tools. And unfortunately, because the acronym RCS is already taken by a specific implementation of a revision control tool, there's a clash there, so some people use version control systems instead. All right, so why would you ever want to use SCM for tracking your code changes? So there are a couple of things. We track history in revision control systems so that if you ever make a mistake, you can go back to your previous point when something was still working. The revision control systems open up a way to do parallel development. And this basically means that you can have multiple branches of development, one stable, one experimental, or maybe you have a branch for a particular release for a client, and you can continue developing in all of those in parallel, adding changes to each stream as if it was a different project, and then flip between them as you need to, merge changes, and so on. There's also an aspect of collaboration. You can have multiple developers contributing to the same project, and using a good revision control tool, this becomes fairly seamless. And lastly, you get the benefit of having a backup. Whenever you commit your code to a revision control system, if you add a really stupid change to your code, you can always go back to something that worked, or if you happen to delete files, there's a backup. So now I'll go over a brief history of these tools. So shortly after the dinosaurs became extinct, we had Unix. And Unix came with a tool called SCCS. SCCS was fairly simple, allowed you to revision files inside a single directory. It really wasn't meant for multiple developers, and it really wasn't meant for parallel development on multiple branches. Then over the evolution, RCS came. I believe its major contribution was the fact that it was faster. The way that it worked internally is instead of applying patches on top of a base release, it always kept the most recent state of the file available at any time. So when you checked out, that was a fast operation. It also complicated the interface to the tool slightly, so people were complaining it was more cumbersome to use. But it did introduce parallel development because it did have some aspects of working on branches, although it was very hard. In my experience, anybody that's ever worked with these tools always wrote complicated shell scripts around them in order to actually be able to use them. But at this point, we didn't really have any collaboration yet. We couldn't have multiple developers working on the same project in a fairly easy way. So that's where CVS came in. And CVS introduced a way of collaborating between multiple developers and working on the same project. So that was all great. However, CVS had some really big drawbacks. So the guys that worked on Subversion came up with Subversion to fix those three big issues. And the three big issues were you couldn't revision directories, branching was horrendously slow on big projects, and the third one was that commits were not atomic. So atomic commits, whenever you have multiple changes that you're making to different files, you usually want to keep them together. So when you issue a commit command and you're storing the state of your project, you want to make sure that they're together, so later on when you go back to this point in history, you're actually getting all your files across the whole project, not just some files from one commit and other files from another commit. Then shortly after that, we had a new kind of way of thinking about revision control, and these were distributed or decentralized revision control systems. The first generation of those was GNU Arch and Monotone. Arch's claim to fame was that it was very difficult to use. It had a very wide and weird command set, lots of options. It was difficult for newcomers. Monotone was not like that. However, it doesn't scale very well. The architects of Monotone decided to use SQLite for the back end of Monotone. And while that's great, it doesn't really scale quite well. Darks came out after that, and it also introduced something new, and that was patch dependencies. Whereas with other revision control systems, you would be adding commits onto a particular line of development, it was fairly linear. When you're dealing with darks and you add a new change or a new patch to the system, you can think of it as a bag of commits. And you pull out a patch that you want to work on, and it pulls out of the bag all the commits that this particular patch depends on. So these patch dependencies basically are pointers from certain patches to other patches that are dependent on the commit you want to work on. So finally, we get to Git. In 2005, Linus Torvalds, the author of Linux kernel, started looking for a revision control system. He went through all of the ones that were currently available, decided none of them would scale to what he was expecting. There are thousands of contributors to the Linux kernel. Many lines of code are being changed daily. I don't remember the specific numbers, but it's like in the hundreds of thousands of lines of code are being changed weekly or even daily on average. So Git was designed to scale well. That was its goal. Around the same time, another kernel hacker, Matt McCall, got into a heated debate with Linus when Linus was designing Git. And they talked about the internal structure of how the metadata should be stored on disk, and they completely disagreed on the format. So Matt wanted to prove Linus wrong, and he started his own tool. That's kind of how Mercurial came to be. Mercurial is a very good tool. I prefer Git because of the mind share. Usually all the new features or all the new workflows come out of Git, and they're usually copied in other revision control tools. The third one is maintained by Ubuntu. And this is actually an evolutionary chain from GNU Arch. GNU Arch became GNU TLA, and then TLA converted into Bazaar NG, and then Bazaar became Bazaar. So it's yet another tool. Of the three, it's definitely the slowest. They claim it's the easiest to use. I'm not really convinced. All right, so as a review, the first two tools were useful for single developers on a single computer, no collaboration, very little support for parallel development. The next section are revision control tools which require a single database, and all the clients communicate with that one single database. This is centralized revision control. And then the next group are distributed. What that means is you can have multiple servers hosting the same repository. They could be at different states from each other. It's not like they're replicating each other instantaneously. And this means that different developers could host their own forks of the projects and work on different subsystems. At some point, people merge together. So these are distributed revision control systems, and that's what I'll be talking about today. So let's talk about components of these systems. So these are the three building blocks of what's in a revision control system when you're working with it on your box. So a working tree is just a tree structure. If you have a project, you have files, they're inside directories, you already have a working tree. If you don't have a revision control system, that's all you have, right? You're working on your project. Then you have the repository, which you can think of as a database that maintains the history of the project. And it keeps track of file contents. And somehow we need to represent these. Git stores them inside objects that are called blobs. Sometimes you store them as patches to previous revisions in various revision control systems. Git actually chooses to store the entire file in a zipped format and uses the fact that gzip is very good at detecting redundancy to reduce the overhead of the file storage. So if you only modified files ever so slightly, when you combine them all into one stream and then you zip it, it's going to detect the redundancy and compress it. All right, so when we group multiple files together into one state of the project, that's called a commit. So at any given time, the files in my project are in a particular state, let's say version 0.1. I'm going to capture this state in a commit. I'm going to describe what I've done to get to the state. The revision control system is going to tag this with my name as being the committer. So that's the who, and there's a when. Is that legible? Yeah. And then there's a when describing when this commit was created. So over time, we're going to build up more and more commits, and we're going to build up something that's called an ancestry. Ancestry also has pointers, which identifies which commit came prior to the one we're looking at. So the top commit is the most recent, the bottom commit is the oldest, and we have arrows pointing to the parents. All right, so I'm going to shrink this down a little bit. So we also have branches of development, and this is our parallel lines of development. So here we can see that at commit B, 2 different developers or the same developer for 2 different reasons branched our project into 2 different directions. So C and D are probably not related, and they're different lines of development. So eventually we're going to merge our commits together. So here we have a commit F that merges 2 separate branches of development together, but we don't have to merge everything. So here we have 2 branches again, the one represented by I and F, and we're not going to merge them. And in this case, this repository is sometimes referred to as a multi-head repository or a multi-tip repository. The commits, which are the youngest on any particular branch, are sometimes referred to as heads and sometimes as tips. So we're pointing to the parent. Every commit points. The question was why the arrows are pointing down against the timeline. So we're pointing to the parent of the commit that came before it. I believe actually Subversion does it the other way around. All the distributed revision control systems do it this way. So from the branch of mathematics called graph theory, this is referred to as a DAG, or a directed acyclic graph. A graph is just a flowchart in mathematical terms. And directed indicates that the edges have a direction, so the lines connecting our nodes have a direction. Acyclic indicates that if you start from any particular node, you follow the arrows, you can't get back to the same one. There are no cycles. So I'm going to refer to this as a DAG in the future. We also have references into this DAG, not just commits. And these references are pointers. We have 2 different kinds, tags and branches. And the distinction between tags and branches is usually with how you intend to use them. So a tag is something that usually represents a commit forever. You never want to change it. Once you've released the project version 1.5.0 in this case, it doesn't make sense to now point to a different commit with the same symbolic name. So tags stick to commits for the rest of their lives. Revision control systems usually let you move tags around, but the intent is usually to just stick with one commit for a tag. And branches move with the development of a branch. So if we look at topic B branch and we add a new commit to it, we can see that the branch advances with it. So also in Git, we have another term that's a reference, and this is called a head, and it represents the current checkout. So we have a special kind of tag, a special kind of reference, which points to a branch. And this is the branch we're currently working on. Git repositories can store multiple branches on in your local checkout. So you can have multiple branches, as we see here, and we just need to tell which one we're currently working on, and that's called a head. So you can have multiple heads, but only one of them is called the head. All right, so that's the current checkout. We also have a staging area, and these are the things that we want to commit when we run the git commit command. So certain revision control systems will not actually claim that they have a staging area, but if you've used Subversion and you issue the svn add command, well, Subversion has to stage that somehow. It has to remember that the next time you run svn commit, you actually want to commit some changes. In Git, we're tracking 4 different things in our staging area. We're tracking new files that we've added to the staging area, removed files, renamed files, and things that we've changed, and we decided to commit. All right. The question is about how Git represents moves internally. There is a Git move command, Git mv, and I don't have slides for it. But actually, this is a better question for the next talk. Were you planning on attending the workshop? Yeah. Okay, so how about you ask me that question when we get to the workshop? All right, so this is more specifically a talk about revision control systems, so I'll defer that question. All right, so workflows. Workflows represent steps that you repeat over and over again in revision control systems. Like, for example, you stage a file, you commit a file, right? You edit the files in your working copy, you make a commit. And you repeat this over and over again as you're developing your project. So these are kind of workflows. And traditionally, the way that development was being done is you would have a trunk. And trunk was your main line of development, and it represented multiple developers working on what's going to become the next release. So here we could have a feature that's actually spanning commits L and O done by one developer, while the other developer concurrently is working on M and P. And as they were committing their individual parts of the features they were working on, they could actually become interlaced with each other. And of course, once our project became stable, we would have branches for particular releases. Like here we have version 1 and version 2. So these commits are usually fixes. Because once we've released version 1, there might be new bugs which we want to release as updates to version 1. Like, for example, version 1.1 and so on. So the branch here is called version 1, but there might be tags within it which indicate updates to that particular release. So these are fixes. And most likely the things that are going on the trunk are major features. We rarely do feature development once we've released. So this is the traditional model of version control. When you have a revision control system which has very fast branching, like most distributed revision control systems have, then the world opens up to different kinds of workflows. One common one is a topic branches workflow. And the idea here is that you isolate your features in individual branches, and then when they're finished, you merge them together. So we have one branch per topic. We're going to commit very often to this particular topic every time we're advancing the state of the repository. They're short-lived because we delete them as soon as we merge them into the master branch. So master is the default name for a branch in Git. I don't think there are other revision control systems which have multiple heads, so they usually don't have a name for their default branch. In Mercurial, sometimes it's referred to as a tip, but they only have one branch, so you seldom use that name. So let's go through an example. We'll start with a repository with 2 commits, and we'll have our default master branch in our Git repository. So we'll branch for a feature, because there's a particular feature that we want to do some development on. We'll do a commit on that feature. We'll switch to a quick branch because we've noticed as we were developing this feature that there's a bug we want to fix. So we'll fix that bug. It only required 1 commit. And then we go back to the feature development, and we're going to merge in that fix because continuing development on this feature relies on this being fixed. But we actually fixed that bug on a separate branch because that was the topic for that branch. So there was a quick topic. All right, so then our boss comes into our office. Customer got a beta coming off trunk, and it's broken. It's crashing or something. So we have to fix it immediately. So we basically put all of our feature work aside, and we work on this particular fix. So we're going to, first thing we want to do is we want to pull in the changes that the other developers have done on the project that actually causes this crash, presumably, or maybe it was done further down in history. And we're going to branch off to fix this crash. We'll fix the crash if it happened to be fairly easy to fix. And then we're going to switch back to switch back to the master branch and merge in all of our fixes and actually commit them to the upstream repository so that the build guys can build a new build for the customer and they can get beta 2 or something. So now we're going to go back to our feature development, and we're going to continue building our feature. We finish off our feature, we switch to master and merge. So the thing to point out here is the master branch often becomes the integrating branch. It's the one you pull stuff into. It's the one that you share with the other developers from. And why would you want to do something like this? Well, you get better visibility of where the feature was being developed. I encourage everyone in this room to commit very often, and so you will have lots of commits for a particular feature. Working without committing means that you can always lose some good changes. Like you're working on a project, you make some good commits, then you make a stupid mistake which actually ends up removing some good code. Well, if you didn't commit before you made that stupid mistake, then you can't go back in your revision history. Going back with revision control systems is always cheap, even with centralized ones. It's cheaper than rewriting the code again. So commit often. If you work on topic branches, it's still easy to see why all of those commits are being committed together. It's for this one feature. And it slightly improves code review. If the intent of the code review is to look at the individual changes as they're being added, since, again, they're isolated in their own silo, so you can review that one particular feature at once. In a corporate environment, there might be a policy that no code gets into the trunk, the main line of development, unless it's been reviewed. So, for example, this feature, before we could merge it into master, maybe it wasn't allowed to be merged in yet. So there could be a policy that prevents that. And I think I touched on this already. You're delaying your merge decision. You can have multiple feature branches. Some of them could be finished. Some of them could be in other states of development. And if you're not interested in merging it together, you can decide at a later point, just before a release, that feature A and B get in, feature C doesn't. All right. So, yes? Right. Usually tests are shipped with the repository, because if the repository that contains, let's say you separated them, and you had your unit testing suite in one repository and your code base in another, and they diverged, so you're working on version 1.0 of your code, but version 2.0 of your unit tests, you're going to have a lot of failures because you don't have these features in your repository. So they're usually kept together, and as you develop your features, you're also developing your tests concurrently, either before or after your features are done, to help you test them. So they're usually kept together. Now, I can answer the Git portion of this question. When you're creating like a zip file or a tarball of your project to do a release, is that what you're asking? To ship the source code, or you mean to share it with the rest of the community? Okay, so exactly, yeah. So you do want to keep the tests in revision control, because you do want the other developers to run these tests. So that's not the problem. The problem is when you create a finished product, assuming you're shipping source, you have a tarball or a zip file, and you submit it on the website, and people that download this. Git has a feature called Git Archive, which generates these archives, and you can ask Git Archive to exclude certain directories. So I guess this could be one of the uses for that, is to remove the test suite. Okay, so now we'll talk about centralized development, how it all looks, how the systems interact. Just a quick review. We have a server. The server contains our repository, our project state in a DAG. It has its own repository. The clients only get a working copy. So here there's the directory tree with the project that we're working on. And the clients come along, they make a connection to the server, and they can issue read requests, things like checking out a project, so creating a working tree on their system. You can update it from the server. You can create diffs from any commit on the server with your working copy or between two different commits on the server. And you can look at the log or the history of the project. Then you also have write commits, things that generate, you have write operations which generate new commits, create branches, or create tags that change the state of the repository. And if other developers come along, they too can make connections to the server, and they too make the same kind of operations, right? So the thing to point out here is that we need a server to operate. If the server happens to go away for some reason, none of these guys can collaborate unless they send each other emails with files. So there's a single point of failure, because if we lose the server, we can't collaborate, we can't advance the state of the project, we can only work on the code in our working tree. And it becomes a bottleneck because all of the accesses are serialized. So this obviously only matters to very large projects, but you have to wait for the first client to finish doing the merge or the update or whatever before the next client can connect and do a similar operation. All right, so decentralized SCMs is what I'll talk about next. So we'll start off, we have a server just like before. We have a client just like before. The client comes along, and he does a clone. What a clone does is it replicates the repository that's on the server to their own system, and it creates a working copy in which they can work. So the working copy is just like we had before. The thing that's new is now every client has a clone of that entire DAG on their system. They can issue local operations, like all of the things we've seen before, like committing, branching, tagging, updating their working copy from the repository, checking out files. All that stuff is all done locally without any network interaction. When they actually want to update their repository with whatever somebody else committed or put on the server, they will issue a pull operation. A pull operation is a read-only operation. It gets the latest things from the server, and it updates our local copy of the repository. All right, so then we have a push, which does the opposite. It takes the changes we've made in our repository and publishes them to the server. When new developers come on, they also can do pull, push, clone, whatever, to the server. However, while the clone and pull operations are read-only, a push is a write operation. And when you're working on open source code, you really want contributions from everybody, but you want to have the final say of what gets in. So you may want to remove everybody's access to your repository so they can't push. They can still clone the repository. They can still update their repository from the server, but they not necessarily need to push to the server to prevent them from committing garbage into it. One thing that distributed revision control systems allow you to do is, in the absence of a server, developers can collaborate just between their laptops. Somebody can run a server that listens for connections on their laptop, and now you can get people pushing to your laptop. Probably also a bad idea. So what we can do instead is enforce that all of the non-trusted entities, or not the original author of the project, has pull access. Grants pull access to the original author. And now the original author can pull from the contributor and get updates from them, merge them into their project, and then push them to the repository on the server. So this works fairly well. But the thing that I want to point out here is it doesn't matter where the server is, because really the only thing that distinguishes a server from a client is the server doesn't have a working copy because no code is actually being generated there. It only stores the repository. So anyone can have a server. And the benefits of these are, here are the 5 benefits, though I'll go through. So the first one is speed, right? So because you don't have to go over the network, you have much improved, much lower latencies when you're connecting to the repository. If you want to inspect the history of a project, if you want to create branches, tags, if you want to merge, all of these things are very quick operations. They're localized. Also, modern operating systems cache disk pages, which gives you the added benefit on top of the fact that you don't have to go over the network, because once you've accessed your repository, the operating system will pull all that stuff from the disk, store it in memory, and as long as you have enough memory, you never have to go back to disk to do any read operations, right? So if you're doing lots of code review, for example, or if you're doing merges, there might be older commits that you need to pull into memory to do merges or to do review. So distributed revision control systems, because they have all this information locally on the disk, benefit not just because they don't have to go over the network, but also because they keep everything in memory. So the differences we're talking about here is like 30 seconds for a centralized revision control system to close to 0 seconds to a distributed control system. And 30 seconds doesn't sound so bad. The thing that revision control systems improve when they're distributed is they open up the world to new workflows. So people can now work on things like topic branches because switching branches is very quick. People sometimes complain, well, they raise a fault to distributed revision control systems that they clone the whole repository. So isn't it bad that you're cloning all the history from the server? So here's a comparison. There's a project I work on for one of my clients. They have 24 megabytes of source code, 2,000 files. There are 55,000 commits in the history, and Git reports there are 110 objects. So everything you saw in the DAG is an object. Commits, files, everything is an object. So doing a Git clone, which gets all the history from the last 6 years, took 20 seconds with Git. With Subversion, it took 40 seconds to clone this over no network access because I was actually on the same machine. So while I was communicating over network protocols, they were just going over the loopback. So even with no network access to like SourceForge.net or some kind of a hosting site, there's a big improvement here. So cloning, getting the whole history, it took Git less time, half the time, than getting just the most recent checkout with Subversion. Again, Git's like designed from the ground up to be fast. So actually, here's a comparison showing how much disk space was used after the clone and the checkout was finished. So for 24 megabytes of actual source code files, it took Git 92 megabytes of disk space to get the repository from the server, right? So there's like 70 megabytes of overhead here. I don't know where Subversion gets its overhead because it took it 81 megabytes just to get a single revision. Here's a comparison of switching branches. Again, if you're using topic branches, this is fairly important. So switching between two similar branches is when you have two branches which are fairly close together, so the diff between them is fairly small. There are some statistics on the bottom which identify what I mean by similar and different. And different in this case are two releases that were 3 years apart in development. So it takes Git almost no time. Those are the green numbers to switch between branches. It scales very well. It doesn't matter how big the change is because it doesn't have to get the deltas over the network. Subversion, a lot more overhead. All right, so another benefit is non-intrusive microcommits. And what non-intrusive microcommits are is a way to committing very often and small changes. That gives you the microcommits. So you can always go back to the state you were in 5 minutes ago or half an hour ago when things were still working and before you broke something. Whoops. And the non-intrusive means that while you're doing this, you're not necessarily breaking the build for anybody else. This can be achieved with branching, even in a centralized environment. But there are some problems with a centralized environment and branching. If every developer, and you have hundreds of developers, creates a branch on the Subversion server, you have a lot of pollution of namespace. You have lots of branches from Bob and Joe, and you don't necessarily know what state they're in. You need Bob or Joe to tell you what state they're in. So you don't want to create them on a centralized server. You want to have these topic branches on your local machine. So you never break the build because you don't push stuff into the server until it's finished, which is how most Subversion users would work anyways. They would work for a week on a big feature, and then they would commit. At least so is my experience in the corporate world. All right, so you can also revision your experiments, so things that you're not really sure are going to work. These are things that you may not want to put into Subversion or a centralized revision control system because you don't necessarily want people to start having crashes that you don't expect. And then if you don't like something, you just remove the branch from your local machine, and it's gone. So detached operations. I actually used to do this a lot when I was working with BitKeeper, which is a proprietary revision control system that's distributed. I would work on a train. I live in Ottawa, and the company I was working for was in Toronto. So every couple of weeks, I would take the train down to Toronto and do integration. But I had 2 hours to kill on the train, about 2 hours. So I would code. And I could still make commits. I could still look at other people's work, do code review, because I had all that history on my machine. Right? So at the companies I've worked at, we usually freeze branches. And freezing branches happens before a release. It usually gives QA some time to do extra tests, deployment tests, stress tests, whatever, and it prevents developers from committing to that branch, even if they're fixes, right? So you can still develop and make these micro commits on your branches, even while the branch is frozen for whatever reason, if you have a distributed system because you have those branches locally. If your VPN happens to break, same idea, right? You can still work on your laptop at home. You can also collaborate. So if I was traveling on a train with a friend of mine, we can use a USB stick or a Wi-Fi connection to share data between each other with a distributed revision control system because we both have that history. We just have to pass the commits between each other. And there's no single point of failure, so if the server melts down, and actually this happened a couple weeks ago at a different site, the system on which the revision control was being ran died, and it took like a day for the IT people to find the right backup tapes to restore the revision control system. So basically, for that one day, there was a slowdown to progress of developing the project. And backups are trivial because any developer that's ever cloned your repository has a backup up to the last point that they talk to the server. So everybody has a backup of your project. Right? So next, I would like to talk about topologies. So these are the ways that you interact with other developers when you have a distributed revision control system. So we'll start with a single developer on a laptop. They have their repository, and they have a working tree, and they're going to be making read and write operations between the working tree and the repository. Eventually, they will want to publish their work, and there are lots of hosting services. Just like you can host a website, you can host your project, your source code on a system that stores your revision control system. And this works both for distributed and centralized systems, like SourceForge for a decade was hosting CVS and Subversion projects. So now there are new hosting services which provide Git, Mercurial. So Git, a famous one is GitHub, for Mercurial, there's a famous one called Bitbucket. There's Gitorious for Git. For Bazaar, you really want to stick with the Ubuntu stuff, so you want to use a site like Launchpad, which is run by Ubuntu or Canonical. Anyway, so there are lots of sites that you can choose from to publish your work. In a corporate environment, of course, this would be on a corporate server behind your firewall. So we issue a push operation, as I mentioned before, to take our repository from the client machine and publish it on the server. So now we have a complete copy of whatever was on my laptop on the server, or a subset thereof, if that's what I decided to do. If another developer comes along, a contributor, what they can do is they can clone my repository from the server that I've published. And now they have a complete representation of that repository on their laptop, and they get a working copy with a checkout of whatever happens to be the most recent commit on the master branch. And when they are done making their contributions, one of the choices they have to sharing those with me is to email me the changes. So revision control systems tend to work on diffs, which I'll show in the second part of my talk. A diff shows you the differences between two different commits. You can email that diff, it's just text in most cases, to one of the other developers. So in this case, we have a contributor adding a new feature, fixing a bug, and sending a patch to the original author. The author can then take that diff, apply it to the repository, and everything is great. However, it doesn't scale very well on larger projects because you will be getting lots of emails. Emails could be lost. So one other thing you can do with the distributed system is that developer could have their own server, or they could have a repository on a hosting site, or they could use the same site as you're using, right? And they just need to email you with the URL of where their repository is. Oh, sorry, skip the slide. First, they push their work onto that server, and then they ask you to pull from that repository, and then you integrate their work into the project. You commit it to your server or your repository on the server, and the cycle flows, right? Another topology is a centralized one. So this is very common for companies that have adopted distributed revision control systems, but are still using the centralized model while using that distributed mentality, or using a distributed tool with a centralized mentality. So here we have a single server in the company. All the developers are now cloning that repository onto their laptop, so they have the benefit of having all the history on their laptops, and they can go home and work there without a VPN connection if it's not available, and then they can come back to the office and sync up with the server. So not all individuals in the company or not all systems in the company need to have write access to that server. For example, we might have a build server that only needs to clone or check out repositories. It doesn't necessarily need to commit because build servers usually don't do that. They might tag, in which case they would need write access. And we might have backup servers which just clone that repository onto another machine, so there's a backup. Yet another topology, sometimes called gated or an integrated topology. So here we have some developers on a server, usually inside a company, but it could be adopted by an open source project too. And and on the server, we have one blessed repository. So this is a repository from which everybody, this is the repository from which builds happen. And anybody can clone and pull this repository and get a copy of the project on their system. However, there is a special individual that's the integrator or a gatekeeper, and what they are permitted to do is also push. So not just pulling, but they're also permitted to push. The developers, on the other hand, have their own repositories on the server, and they integrate between each other, but they mostly work within those repositories. So they have their own topic branches. For example, one developer is working on a feature, another developer is working on another feature. They would have those feature branches in their individual repositories. If they happen to integrate between each other or with each other, then they could share the other person's topic branch in their repository and pull from each other. Usually, pushing is not necessary to a neighboring repository. You just push to yours. But eventually, the integrator will take all of the finished work that the developers have claimed is now ready to go for the next release. They will integrate it. Maybe somebody will review it. There'll be some testing. And then they will push it into the blessed repository, and then we get a build. So there's a more complex version of the last example, and here we're just adding another tier. And this is the way that the Linux kernel is being developed. Like I mentioned before, thousands of contributors are committing changes to the Linux kernel, so we need an extra layer to lessen the workload on the individual integrators. So here we have Linus with the white laptop, and he pushes to a single repository where he stores his work. He publishes a kernel, and anybody is permitted to clone that repository from Linus to get the latest work. We have certain developers which might have their own servers or might have repositories elsewhere. They're special. They're called lieutenants. Lieutenants are responsible for individual subsystems of the kernel, like let's say networking or security subsystem. And what they are interested in is making sure that that part of the kernel works really well. That subsystem is good. So they might publish their own repositories on a different server or the same server. And some developers may actually want to continue to work on those branches as opposed to Linus's branches because there's something new in there that they want. So let's say there's a new fancy driver, and this particular lieutenant happens to be maintaining that subsystem. They may continue working on that driver, which is not yet available in Linus's kernel, but it's available in the subsystem. All right, so eventually the contributors finish their work. They might send patches to the lieutenants, or they might submit patches on the mailing list, asking them to integrate it. The lieutenants take it into their trees. Some developers might use a hosting service like GitHub to publish their work if it's a larger contribution. The lieutenants integrate the changes and email the dictator asking the dictator to merge their work. So at this point, all of the review and the testing has potentially been done. Linus doesn't scale to having 12 lieutenants and hundreds of developers under each lieutenant, and you can't review all the work. So we actually trust the lieutenants of the subsystems to do their job, to making sure that all the components work, and of course on peer review on mailing lists where every single line of change is looked at. So once that happens and Linus decides to integrate individual features, then he will commit them back to his repository on the server, and the cycle continues. Oh, so I guess I'm done. All right, so since we have time, I'll be going into a quick overview of Git commands. So if you've used Git before, you will walk away with nothing here. But it might interest you into coming into the workshop. All right, so we'll talk about initialization commands first. So in a centralized system, you rarely create your own repositories. Most people don't run their own Subversion repositories unless they're inside a company and that's their job. They usually use things like SourceForge for open source projects, or maybe other hosting sites for closed projects. And they email the administrator or they use a web UI to create a new project. What happens behind the scenes is it runs a Subversion SVN admin command with the create option, creates a new repository. With Git, there's a lower bar of entry. Creating a new repository takes like, I don't know, 1/10 of a second, if not less. It basically creates a .git directory and a working tree, populates some empty files in there or some default files, and it's done. If you have an existing repository on the internet that you want to use, then with Subversion, you use the checkout command. You check out a URL. You have a working copy on your system. We saw git clone before. Git clone is the command that takes the repository, replicates it on your machine, and it checks out the most recent version of master by default. Then we have the modify commands. Yes. My answer is this. The question was where the metadata files go inside your project. So inside your working copy, there's only a single .git directory, and I have slides for that in the workshop. Yeah, so then we have modify commands. These are things that modify the state of your DAG. So we can add, delete, rename files, and Subversion has add and remove, and you can kind of mimic a rename. And Git introduces a move command also, which does a rename, so it's fairly similar. Making commits with Subversion, use the svn commit command, and you specify some files. We have a git commit command also, and it does almost the same thing. The only thing that's different, and why I included the -a, is the default behavior of Git is slightly different. When you run svn commit with no changes, it commits all the modified files, which Subversion is aware of being in the repository already. When you run git commit by default, it commits what's been staged. If you run git commit -a, it does the same thing like Subversion. It commits all the modified files. So slightly different, but almost the same. Information retrieval. So if you have a working copy and you want to figure out what you've changed in the system, SVN has a status command, Git has a status command, almost the same idea, slightly different output. If you want to compare two different revisions or compare your working copy with another revision, you issue a SVN diff command, and this compares two different states of your project. Git, diff, same idea, actually almost identical output. And if you want to look at history, I never liked this command because I find it really difficult to use. It just presents on a long-lived project. It gives you such a horrendously long output. You always want to get the first 10 lines. With git log, it actually by default passes it through a pager, so at least you see the most recent commit before it runs off the screen. References, so you can tag commits, and we do this by emailing the build guy, because in a corporate environment you usually don't create tags, and the build guy runs this command, which I don't know why there's no tag, but there's a SVN copy command. I do know why there's no tag. The way that Subversion is architected is the distinction between tags and branches is very small. So you have a namespace where you create your references or your branches or different lines of development. And by default, you have a trunk directory inside this namespace. But you can also have a tags directory or a branches directory or experiments directory, whatever you want. By default, you stick tags inside the tags directory. So that's the command you have to issue. With Git, there's a slightly lower bar of entry here. You just do git tag and give it a name, and you have a tag. Branching, Subversion, same idea, right? You don't branch. You call somebody else. You get them to branch. It's the same command. You can see there's a difference there between tags and branches, just a different location in the namespace. And git branch is you just specify a name. It creates a new branch for you. So switching branches. With Subversion, you issue a Subversion checkout command, Subversion switch command. With Git, you issue a Git checkout command. It's called Git checkout here because you're checking out a different state from your repository into the working tree. So it's the same as doing a checkout from a Subversion tree, from Subversion repository into a working tree. And merging. I really don't like merging in Subversion. Merging the first time is not so bad. Merging subsequent times gets complicated, and you can end up with command lines that look like this if you want to merge two branches together. With Git, you just specify a name, and the merging is fairly seamless unless there are conflicts. So distributed operations don't have a centralized equivalent, so here I'll just show you the Git ones. So we already saw Git clone. You specify a URL or a local path on the disk, and you get a new repository or a new working copy with a repository, and you work in that. If you want to update from a server, you do git pull. If you want to share with somebody else, you do git push. And that's my last slide. So you already know how to use Git, and I think lunch is coming up at some point, right? So we'll head out. Thank you for coming to my first part of the talk. I wanted to remind you that I have another part after lunch that actually talks about how to use Git. Not so much about these basics of distributed revision control systems. And if you have any questions, then I'll take them now. Here are some URLs. If you want these slides, write down the short URL in the middle of the slide. You can get them from there. There's the official URL for the Git revision control system where you can find lots of documentations and books and so on. Thank you. I'll talk about this in the workshop. Git separates so because we have multiple heads in our repository, let me find a slide that works with that. That'd be something, right? Okay. Okay, so we saw this where we had our line of development and the server is somewhere up advanced, right? So if we pull into our repository, what pull does is it gets all the references from the remote server and then it merges them with whatever work we have on our system. If we didn't do any new work, there's no merge to be done, so it just updates. If we've done some work, it also merges. However, you can just do a fetch, which is a half of the pull. And if you fetch changes into your repository from the server, then you don't merge. So now you can fetch, inspect what the other side had, and then decide if you want to merge. So you can split the pull into 2 steps if you want to do code review before you merge. And I have an example for that in the second part. Unfortunately, yeah. An Eclipse plugin, there's a pure Java reimplementation of Git called JGit, and it's like a library with an API. And there's an eGit project which uses JGit to implement a plugin that goes into Eclipse, which then communicates with a Git server. So everything is inside the Eclipse environment. I don't know what tools they have because I've never used it. I'm a command line user, so I can share with you how Git works internally and the names for operations that you'll be using, but I can't tell you how the tools look when you're using them. What time's lunch? Am I early?
If you guys have any more questions, we still got a couple minutes, but lunch will be over in Siebel. If you have your badges, you can get some lunch.
Did you learn anything? It's the same like the first part of my other talk, right?